So our project is to apply quantum machine learning model for the disease grading of Indian diabetic retinopathy. And in this problem, we have used the Indian diabetic retinopathy dataset. For quantum machine learning, we have used a Panelin library. First, we are installing it and then we are importing it. And then we are also importing some other important libraries like a TensorFlow and Matplotlib, etc. Now we are setting some main hyperparameters like the number of epochs, number of layers, number of training dataset, testing dataset, etc. Now we are loading the dataset. So basically we have a Indian diabetic retinopathy dataset in which we have a image name and the respective class. We have total of 5 class 0 to 4. Now we are adding path to our image name so that we can actually get the image from the desired path. Now we are splitting the dataset into the training and testing dataset. Now we are making a tensor of 224 by 224 from the image of 224 by 224 pixels so that it can fit to our model, which we will define later. We are repeat this process with the testing dataset. Now we are normalize the dataset to fit our convolution channels. We are also putting one extra dimension for our convolution channel. Now we are defining the convolution circuit as a convolution kernel. So we first initialize the Panelin qubit default circuit and which consists of simulating a system of 4 qubits. The associated Q naught represent the quantum circuit, and this circuit is consists of an embedding layers of the local RY rotation with an angle scale by a factor of pi, which you can see here, and a random circuit of n layers. Now we have the final measurement in the computational basis, which are estimating the 4 expectation values, which you can see here. We have a final measurement with the 4 expectation values. Now moving forward, we are going to define the convolution scheme. So we have images, and this images is divided into the square of 2 by 2 squares pixels. Now each square is processed by the quantum circuit. The 4 expectation values are mapped into a 4 different channel as expected, because we are expecting the 4 expectation values, which you can see here. Now we are moving to the quantum processing. So since we are not going to train the quantum convolution layer, so the more efficient way is to apply the pre-processing to all our data set which we have, and later we will define the classical model and fit this pre-processed data set to the classical model, so that we don't have to again and again train the quantum layers, and we are basically save the quantum computations. So we have the pre-processed image, and which we can save once, and we can use again and again without pre-processing again, because this process is consists of so many computation. So this process is shown in this code. So we are doing this process with the train and test dataset, and we are saving it as this .npy. Now let's visualize our image. So as you can see here, we have an input image, and we have a 4 expectation channels, as we have discussed in the quantum circuit, which is represented by this grayscale. So we can clearly notice that in the output of the 4th channel, we have a very downsampling resolution, and we have some local distortion which is introduced by the quantum kernel. On the other hand, the global shape of the image is very preserved. So 224 by 224 pixel is very preserved for the convolution layer. Now we are defining the hybrid quantum classical model. So basically we are defining a classical model, and in this model we are applying our pre-processed quantum dataset. So after the quantum convolution layer, we will feed the features into the classical neural network. So convolution layer is basically pre-processed dataset, and we will train it for the 5 different classes of our diabetic retinopathy dataset. So basically here we have just a very simple fully connected layer with the 5 output, and final function is the softmax probability function. So this model is also compiled with the stochastic gradient descent optimization and cross entropy loss function. And here is the training for our quantum convolution network, which consists of the quantum dataset and classical layer.